In this video, we're going to learn about resistance and resistivity in electric circuits. The definition of resistance is as the ratio of potential difference to current. And potential difference in current were covered in a previous video, so if you haven't had a chance to watch that, you should watch that one first before you get into this video. Resistance is measured in ohms. So that's the unit, and that's the symbol capital Omega for the ohm. The formula resistance, based on the definition, is that resistance is V over I, where resistance is measured in ohms. V is always measured in volts, and I, the current, is always measured in amperes. Practically speaking, resistance is the opposition of the flow of electric current and material. So that's what we think of it as. Now, the definition is the ratio of potential difference to current, but if you want to think about it practically of what's going on in the circuit, it's the opposition of flow of the current. There's a number of different things that would affect the resistance of an object in the current. The first one we're going to look at is length. And so it turns out that resistance and length are proportional. So as the resistance goes up, as the length goes up, the resistance will go up. And when we say two things are proportional, we could say that resistance over length is some constant value. So that's what we could say about proportional things. So the longer the wire or the longer the component, the more resistance it's going to have. Now, if we look at the area, and I'm talking about the cross-sectional area, so the area, like for a wire, it's the width of it, if you want to think of it that way. Now, as the area gets larger, there's actually less resistance. So as the area increases, the resistance actually goes down. And mainly the way you want to think of that is the current, the charge carriers, have more space to pass through. It's similar to, say, a highway with many lanes. It's easier for the cars to pass through because it's wider. So when you're thinking about the cross-sectional area versus the resistance, those are actually inversely proportional. So one way mathematically we could say A times R is a constant. That's one way to show that two values are inversely proportional. Another factor of resistance is the material. So depending on which type of material you have, what type of metal or what type of conductor you have, it has some materials have more resistance than others. So if we look at, something like silver, that has quite a low resistance. So silver is a very good conductor. And another good conductor, but not quite as good, would be copper. Copper here has a little bit higher resistance. And so depending on what material you have, that determines how much resistance that has. And that property is actually referred to as resistivity. And so this is a fundamental property. Sometimes in science we call this an intrinsic property. So it's an intrinsic property of a material, and it quantifies how strongly does it oppose the flow of electric current. And if we want to calculate resistivity, we use this formula here. So we have the symbol, the Greek symbol rho. Now it's the same symbol as density. Density is also using rho. So we just want to make sure we're distinguishing those. But when we talk about electric currents and objects in electric circuits, we're talking about resistivity. That's measured in ohm meters. And then the rest of the formula, the R is the resistance in ohms, the A is the cross-sectional area in meters squared, and the length is measured in meters. And often you'll have cross-sectional areas and lengths in centimeters or millimeters, and so you're going to want to convert those to meters. Just to give you an idea of some resistivity values, you see that both copper and silver have quite low values, right? This 10 to the minus 8, that means it's quite a low value of resistivity. And so that means that silver, copper, they can have an electric charge pass through it. If you think of carbon, graphite, you might have seen demonstrations where, if you color really thickly on a piece of paper with graphite pencil, you can conduct electricity. Now, it's not nearly as good as having silver or copper, but it does conduct. Whereas you look here at something like glass, which is considered an insulator, its resistivity value is huge compared to it. It's many more orders of magnitude larger. And so that's why conductors, they not necessarily don't conduct electricity, they just really, really are resistant to it. And it requires a huge amount of energy to conduct electricity through something like glass or wood or other things. So resistors are components that we put into circuits in order to control potential difference and current and different things like that. And this image shows a couple different types of resistors. You see the color bands on them. There's a color code for resistance. But the circuit symbol, when we draw it in the circuit symbol, is a rectangle. And there are other symbols. Sometimes you might see this in resources. People use that as a symbol for a resistor as well. Not all resistors have constant resistance, and so the symbol we use is just the rectangle with an arrow through it. And this is a variable resistor. And what this means is this resistance, we can change the resistance to impact the circuit. You might want to think of like a dimmer switch on a light, where you can get the light brighter or darker. Often those are controlled with variable resistors. A light-dependent resistor, an LDR, is a special type of resistor where as the light intensity increases, the resistance decreases. And so you want to keep this in mind. So an LDR is a device where as light intensity goes up, if the light gets brighter, resistance goes down. And you want to think of automatic lights or something, right? When it gets dark, you get the resistance goes down and the lamp will turn on. So these kind of are very useful and they detect light intensity. Another very useful type of resistor is called a thermistor. And so thermistor, you might think thermal physics, it's related to the temperature. So as the temperature increases on a thermistor, the resistance decreases. And lots of applications for this. They can be used to control the air conditioning in a room, turn off the AC when the room reaches a temperature, or ovens and stoves. It can sense when the temperature reaches a certain value, it stops providing current. So a lot of really good uses for thermistors as well. The last one you see is called a potentiometer. And a potentiometer changes the resistance as this connecting wire moves left or right. So you can change the amount of resistance because it changes the distance the current has to travel through this particular resistor. Now we're going to get into some examples here. So a current of 31 milliamps passes through a resistor of 2000 ohms. Calculate the potential difference across the resistor. So we had that formula, R equals V over I. This is the definition of resistance. And so if we want to calculate V, we multiply I with R. And so we do 31 times 10 to the negative 3 amps. And we multiply that by 2 times 10 to the 3 ohms. And we get a value of 62 volts. When a variable resistor is set to 250 ohms and attached to a battery, the current produces 24 milliamps. Determine the value of the variable resistor to produce a current of 48 milliamps. Now the thing we have to keep in mind here is we have a battery, and batteries have a set amount of potential difference or a set amount of EMF that they can provide. So first we need to figure out what is the amount of energy this is providing, and then we can apply that with a new current and see what the new resistance must be. So first we need to figure out the potential difference or the EMF of this particular battery. And again, like the previous question, we had V is equal to IR. And I'm going to put ones here because I'm talking about the first scenario. And so V1 we don't know. I1 we're going to say is 24 milliamps. So it's 24 times 10 to the negative 3. And R is the resistance, so that's 250 ohms. And so the potential difference in this circuit is 6.0 volts. So this will remain unchanged. As we increase the current, we need to decrease the resistance, and we can figure out how much we need to decrease it by. So V2 is going to be 6, and then we want to solve for R2. So R2 is equal to V2 over I2. So that's going to be 6 volts over 48 milliamps. And we get a value of 125 ohms. And then this is how we do it mathematically through equations. But if you want to think about this logically, yeah, if I want to double the current, it means I need to half the resistance. And so that's what we ended up doing. A 25 ohm resistor has a 0.6 coulombs of charge passed through it in 2 minutes. Determine the potential difference across the resistor. So we have resistance. We can start, this is the type of question we might want to list out all the things we have. So we have resistance, we have charge, which is Q, and we have time, which is 2 minutes. And we know, and we always want this in seconds, so we're going to call this 120 seconds. And we need to find V. And how do we get there? There's no equation with all of these. However, Q over T is the definition of current. So if current is the amount of charge passing in a given time, we can figure out the current in this circuit, and then we can use the definition of resistance to find the potential difference. So this is 0.6 over 120. So our current is 0.0050 amps. Then we'll go to this equation again. Potential difference is the current times the resistance. So we're going to multiply this 0.0050 amps by the resistance of 25, and we will find the potential difference of 0.125 volts. A piece of copper wire has a length of 1.2 meters and a radius of 0.50 centimeters. The resistivity of copper is 1.7 times 10 to the negative 8 ohm meters. Determine the resistance across this piece of wire. All right, so let's start listing out all the different things we have. First of all, we have the length of the wire, which we know is 1.2 meters. We have the resistivity, so that's that letter rho, 1.7 times 10 to the negative 8. And we have the radius. Now, the radius is not part of the formula. We need the cross-sectional area. But the word radius gives us a clue. It means it's a circular wire, so that we could use the formula for the area of a circle. So the area is pi r squared. And I'm going to write the r in meters, and that way we get meters squared. Before you do any calculations with squaring and stuff, you definitely want to convert to the base unit, the meter, first before you convert. So we got pi times 0.0050 all squared. So the cross-sectional area of this wire is 7.85 times 10 to the negative 5 meters squared. And the last thing we need to find is the resistance. So if we rearrange the formula that has the definition of resistivity, we get that R is equal to rho L over A. So we have 1.7 times 10 to the negative 8 times 1.2 all over 7.85 times 10 to the negative 5, which gives us a resistance of 2.6 times 10 to the negative 4 ohms. This value is quite low, but that makes sense. This is just a piece of copper wire. It's not a resistor. So the fact that the resistance is low is a good thing. So a wire of length L and radius R has a resistance R. What is the resistance of a second wire made from the same material that has half the length and half the radius? Now we could try to think through this logically and go through each step, which will get us the answer. However, I'm going to show you how to do this algebraically so that you can have a little more certainty in your answer here. So the original wire has a resistance that could be calculated by doing rho L over A. Now A is the cross-sectional area, and again the word radius means it's circular, so we could say rho L over pi r squared. So this is our original R value here. So let's set that aside for now, and let's see what would it be for R2. So R2, it says the same material, so the resistivity is the same. The length is cut in half, and the radius is cut in half. So we have pi r over 2 squared. Now if we cut the radius in half, we got to put that inside the squared. So then we can start simplifying this. This becomes rho L over 2 pi r squared over 4. So this r squared over 4 is going to come up to the numerator. So we got 2 rho L over pi r squared. And the reason we set aside that original one is you see this here is the same as that. And so we can replace that with r, so we can have this as 2r. So that means the correct answer in this case is B. A thermistor in a circuit with a battery is shown below. Describe what will happen to the current in the circuit if the temperature increases. Now for a thermistor, if temperature increases, that means that resistance will decrease. So the resistance in that thermistor will go down. And we know that if the resistance goes down, that means that the current must increase because the potential difference will remain the same. The amount of energy provided to the circuit will be the same. So V is constant. So that means that if V is constant and V is equal to I times R, that means if the resistance goes down, the current goes up. So if the temperature increases, resistance will go down, current will increase. Okay, so that's the answer there. In summary, resistance is defined as the ratio of potential difference to current and is measured in ohms. And then physically speaking, resistance is the resistance to electric current, so the ease in which electric current can flow. Resistivity is how much a material resists a flow of charge, measured in ohm meters. And again, resistivity is an intrinsic property of matter, and it just depends on the material. A thermistor is a type of resistor where the resistance decreases as the temperature increases. And an LDR, light-dependent resistor, is a resistor where the resistance decreases as light intensity increases. So that's it for resistance and resistivity.